Okay, so now the next function that we have is basically the secant inverse, the inverse of the secant function. So since basically the secant function is basically defined as 1 over secant x is equal to 1 over cos x, right? 1 over cos x, the domain of so basically the domain of the secant function is basically all the real numbers except that for the values of x for which cos of x is equal to 0, meaning that whenever cos of x is equal to 0, then of course the secant function is not defined. Now if you draw a unit circle here, what you have basically this cos function is 0 here and here, meaning that as at pi by 2 and at 3 pi by 2 and at all the basically multiples of pi by 2. That means that I have to take out all of those points from the domain of the secant function, because at pi by 2 basically cos of x is equal to 0, and then 1 divided by cos 0 is going to be equal to undefined. At 3 pi by 2, basically 1 over cos of 3 pi by 2 is 1 over 0. Again, secant x is undefined. At, for example, 5 pi by 2, 1 over cos of 5 pi by 2 is going to be equal to 1 over 0. And then there, basically, again, secant x is going to be undefined, and so on and so forth. Which means that basically I have to write the domain of the secant function. I can write it as the secant function is basically a function which is defined from basically all the real numbers. The domain of the function is all the real numbers except for all the multiples of pi by 2, or all the odd multiples of pi by 2, meaning that minus all the x's such that x is equal to basically 2n plus 1 times pi by 2, where n belongs to the set of integers, right? So that is the domain of the function. The range of the function is basically, as we saw before, we saw that the secant function, like the cosecant function, gives you basically output for all the values from basically negative infinity all the way up to positive infinity, except for between negative 1 and 1. Meaning that between negative 1 and 1 you have no values there. But at 1 you get some outputs from the function. At negative 1 you get some outputs from the function, right? So what that means is that I have to basically write the function as I have to write this function as r minus basically this interval of negative 1 to 1, and of course it's an open interval because it doesn't include negative 1 and 1. So what that means is that basically that is the secant function. Now, the problem with this this function is of course defined and we have no problem with it. And let me take a look at the secant function here. So the secant function, we said that secant cos has to be secant, okay. 2n plus 1 times pi by 2. Okay. Now what we have, basically what we have here is that basically the secant function. Now the problem with this function though is that basically if you draw the graph of the secant function, so if you write SEC secant of x, what you will get is that you can see that basically the function of course is not 1, 1, meaning that for example the function generates an output of 1 at this point 0 and this at this point 2 pi. The output of the function is the same for all of these points as 0, as 2 pi, as 4 pi, as 6 pi, and so on and so forth, meaning the function is not 1, 1. So we have to restrict the domain of the function to some values. We have to restrict the domain of the function to some values so that the function becomes 1, 1. And then once the function is 1, 1, then we can calculate or we can define the inverse of the function. Now you can of course go for example from negative pi to 0. From negative pi to 0 your function is 1, 1. Or you can go from 0 to, for example, pi. Over here again the function is 1, 1. You can go from pi to 2 pi. Again the function is, and so on and so forth. You can even consider, for example, you can even consider values, for example, from for example 0 to pi by 2. That you can do as well, meaning that there is an asymptote over here. If f of x is equal to secant x, so you can see that at pi by 2 over here you have an asymptote, and then you can even go from 0 to pi by 2, or pi by 2 even to, for example, up to this point which is pi, and then pi to, for example, between pi and 2 pi you have basically 3 pi by 2, and so on and so forth. Now now let's see how they have actually defined the domain of this function. The way that they have defined the domain of this function is that the domain of y is equal to secant x is equal to basically r minus x, or x such that x is equal to 2n plus 1 times pi by 2, and belonging to z, and the range is r minus negative 1 comma 1. It means that the secant function assumes all real values except negative 1 and 1, and is not defined for odd multiples of pi by 2. So let me write this down. This means that the secant function assumes all real values except negative 1 less than y less than positive 1, and is not defined for odd multiples of pi by 2. Odd multiples of pi by 2. Now, if we restrict the domain of the secant function to, for example, 0 to pi, if we restrict the domain of the function from 0 to pi, for example, this is pi, and this is basically, this is 0, this is pi, and you can see that over here at pi by 2, the function is not defined. You get this vertical asymptote here. So if you take this point pi by 2 out, and you restrict the domain of the function to basically 0 to pi, meaning that so if you restrict the domain of the function to basically to 0 to pi and take the pi by 2 out, then it's 1, 1 and onto. Then it is 1, 1 and 1, 1 and onto. With the range as the set, r minus basically negative 1 comma 1. Now, of course, you can basically pick any domain that you want, really, but the way that it's been basically defined is from 0 to pi, meaning that from this point all the way up to this point, and then pi by 2 has been taken out, meaning that you can, for example, just as we have defined this domain, you can define any other domain, like, for example, negative, for example, pi to 0, for example, and take this negative pi by 2 out. Or you can go, for example, 0 to pi and which is basically what we have taken, 0 to pi, and then take the pi by 2 out. This is what we have actually taken. You can go from pi to basically 2 pi and take the 3 pi by 2 out, and so on and so forth. Meaning that any of these domains that you take, basically the secant function is going to be bijective, and its range is going to be the same range, meaning that r minus the open interval negative 1 to 1, right? So basically that's you can say that that's the secant inverse function. Thus the secant inverse function can be defined as basically the secant inverse function as basically the domain of the function becomes the range of the function, which is r minus the open interval negative 1 comma 1, and it has to go to the domain that we restricted the function to, which is basically 0 to pi, for example, minus 0 to pi minus the set containing pi by 2, right? So what that means is that of course this would be the principal, basically the principal branch of the function, but you can just as well do basically, for example, write the secant inverse function and write the range as the domain as basically the range that we had before, which is basically r minus negative 1 comma 1, and then map that to, for example, any other interval that you wish, meaning that you could actually choose, for example, just as we have chosen, for example, 0 to pi, you can choose, for example, pi to 2 pi and take 3 pi by 2 out, right? So this is pi to 2 pi, for example. You can write pi to 2 pi and take and take 3 pi by 2 out. Or instead of this, you can write, for example, negative pi to pi, negative pi to 0, negative pi to 0, and then take, for example, the negative pi by 2 out, and so on and so forth, right? And then corresponding to each of these intervals, we will get different branches of the function secant inverse x, and the branch that comes with basically this particular interval, the branch that comes with this particular interval 0 to pi minus pi by 2 is called the principal value branch of the function secant inverse. So this is the principal value branch of the function secant inverse. So then you can say that, I mean, long story short, you can say that I don't know what I pushed on my keyboard, but okay. So long story short, you can say that the secant inverse function is a function from r minus the open interval -1 to 1, and that goes to basically the interval basically 0 to pi, the closed interval 0 to pi, minus the set containing the element pi by 2, right? And now let's do the graph of this function as well. If you do the graph of this function, you will get basically f of x is equal to secant x. You will get basically this graph here. You can see that the outputs, you don't have any outputs between -1 and 1, and you have all of these vertical asymptotes at pi by 2 and 3 pi by 2, 5 pi by 2, 7 pi by 2, and so on and so forth. And the other way, you have all of these asymptotes at -pi by 2, -3 pi by 2, -5 pi by 2, and so on and so forth. And so what that means is that that is basically the function that you have. So now what we did was that we restricted the domain of this function to 0 to pi, basically, all from here all the way up to here. And now if I draw the graph of the function f of x is equal to, let me do it on the other graph. If I draw the graph of the function as f of x is equal to secant inverse x, so you can see that you will get the principal value branch of the function. That the calculator will not give you all of the branches. Otherwise, you would get something like this. You would get a graph something like this. If the calculator were to give you all of the branches, basically all of the branches reversed or the inverse of all of the branches, then you would get basically all of these branches, as you can see, would be turning, would be rotated counterclockwise, probably by 90 degrees or so. But I cannot establish any link between. I mean, I cannot tell you that for example this is exactly this one or that one, and so on and so forth. But what I do know is that, well, at the end of the day, most probably these branches have been rotated, because you have to do it along that 45-degree line, basically, that line like this. And so of course these are these branches have been are the images of these branches through that 45-degree line, which means that basically this line, let's take a look at the, basically, long story short, to finish my statement, the calculator does not give you all the branches that you see over here. It gives you only this part and this part over here, right? The other parts it will not give you. And if I basically show this line, you can see that basically this line over here, this part over here, which is basically the beginning of the domain of the function at x is equal to 0, basically through this line f of x is equal to x is going to give you this branch, right? And then this branch over here, through this line is going to give you this branch over here, meaning that this branch is actually symmetric. This branch over here and this branch over here, this part, are symmetric about this line, and then this branch and then this branch are symmetric about the same line. And that's basically how this function works. And of course you can see that basically the function, from the domain of the function, we had to exclude all the values between -1 and +1. All these values between -1 and +1 we had to exclude, and that is why basically we had to write r minus the open interval -1 to +1. And then the range of the function is 0 to pi minus pi by 2, meaning that 0 to pi basically gives you 0 to pi minus pi by 2, meaning that you will get, let me draw, most probably you will get a vertical asymptote for this function, if I can actually find it. Let me see if I can find tangent. Okay, so let me see if I can find some help for this calculator to tell me how I can enter an inverse function. Well, it seems that in this calculator, if you simply, the way that you can do this, although I didn't see it anywhere on the internet, I didn't do much search or research, but you have to enter secant x, for example. If you enter, for example, f of x is equal to secant x, then this is of course symbol. So it will give you the graph of the secant function. Now, if you want to draw the graph of the function f of x is equal to secant inverse x, you have to enter your secant, and then here use this key, and then here write -1, and then over here you have to enter x all on keyboard, and will give you basically this function here. And then if I draw the, of course you can see that f of x is equal to x, it will give you this line. Now, as you can see, well, now the problem is that my asymptotes are gone, so there is no point in doing this really. But you will learn how to, probably would be useful to learn how to use this calculator. Anyway, so we said that basically we defined the domain of this function as basically the domain is basically from -1 to r minus -1 to +1, right? So it goes from -1 to +1, and then the range goes from 0 to pi. Basically this must be pi. So this is -1 comma pi. So 0 to pi, and so you go from 0 to pi, but then pi divided by 2 is just not there, meaning that most probably it's going to be some line over here, because pi divided by 2 is some value, like for example 1.7 or something. So if this is 1.4, this is 1.6, it's some point over here, which is which must be some point over here. That's not a part of the range of your function. So that is that basically. Now there are two functions remaining here, which is basically the tan inverse function and the cot inverse function. The tan inverse function and the cot inverse function. So let's talk about these two as well. Now the tan function, starting with the tan function, we have, if you have f of x is equal to tan x, so you know that the function tan x, as far as the domain and range and everything are concerned, basically f of x is equal to tan x is equal to sine x divided by cos x, meaning that wherever cos x is 0, the function is not defined. Now cos is 0 at odd multiples of pi by 2. Cos is 0, because if you have a function, if you have a unit circle over here at basically pi by 2, at 3 pi by 2, at these two angles, and at all the multiples of pi by 2, either negative or positive, or the odd multiples of pi by 2, meaning that at 0, at pi by 2, at 3 pi by 2, at 5 pi by 2, and so on and so forth, at negative pi by 2, at negative basically 3 pi by 2, at negative 5 pi by 2, and so on and so forth. At all of these angles, basically cos of x is going to be equal to 0, right? So that means that the tan function is not defined at these angles, meaning that I have to take all of them out from the domain of the function, meaning that I can write the tan function, or the tan function is a function from basically the set of real numbers minus all of the odd multiples of pi by 2. All x such that x is equal to 2n plus 1 times pi by 2, and basically n belongs to the set of integers, right? So that is basically the domain of your function. Now the range of your function goes from basically negative infinity to positive infinity, which means that basically the range of the function is the set of real numbers, right? And if you want to see the graph of the function, we can of course do that. Thanks to Desmos.com, they have actually created a great calculator, great calculator. Now f of x is equal to tan x. That is your function. If you want to see the asymptotes, you can this calculator is also very, you can do great things with this calculator as well, of course, provided that you know how to work with it. I'm not very fluent in this calculator. Tan x. So you can see that all of these asymptotes are, of course, also there, right? Okay, so basically then the tan function basically goes from this domain to this range, right? And so basically, in order to let me actually move with the text. Now, in order for the restricted to. Okay. Now, about the tan function, basically the domain of the tan function is the set. Basically, you can write the same set as basically as this set here, which is basically the set of all x, such that x belongs to R, and basically x is not equal to 2n plus 1, 2n plus 1 times pi divided by 2, where n belongs to the set of integers. That you can write as well, so that means that you can write tan as this domain, and the range of course would be R. So what this means is that basically that the tan function basically is not defined for odd multiples of pi by 2. Is not defined for odd multiples. Is not defined for odd multiples of pi by 2. But then the range goes from negative infinity to positive infinity. Now, if we restrict the domain of the tangent function, for example, to negative pi by 2 to pi by 2, which would be basically some negative pi by 2 would be here, pi by 2 would be here, then of course in this domain the function is 1, 1. Otherwise, for example, if you go from 0 to, for example, this is pi by 2, this is basically pi, this is pi by, sorry, this is 0, this is pi by 2, this is pi, this is, for example, 3 pi by 2. If you go from 0 to, for example, 3 pi by 2, of course, in this domain, for example, the function is not 1, 1, and so the function is not invertible. Now, if we restrict the domain of the function to negative pi by 2 to pi by 2 in this domain, of course, the function is 1, 1. And also onto, and with the range as R, of course. And of course, you can basically, the tangent function can be restricted to any interval, for example, from negative 3 pi by 2 to negative pi by 2, means that, for example, negative 3 pi by 2 would be here, negative pi by 2 would be here, or negative pi by 2 to pi by 2, or basically pi by 2 to 3 pi by 2, and so on and so forth. And still the function would be bijective, and so basically you could find the inverse of the function in those domains as well. So let me write these down, and then we will get to the rest of the material here. So what I can say is that basically if we restrict the domain of the tangent function, if we restrict the domain of the tangent function to, for example, to negative pi by 2 comma pi by 2 to this interval, and of course you can see that this is an open interval of negative pi by 2 to pi by 2. And one thing which is important about writing things down is that, for example, as I was reading the text, now I understand that I was not paying attention to the fact that, for example, the function is not actually defined at pi by 2. So I cannot say that I cannot say that I'm going to restrict the domain of the function to negative pi by 2 to pi by 2 and write it this way. This would be wrong, because then I would be including negative pi by 2 and pi by 2 in the domain of the function and as well. And at these 2 points, the function is not defined, right? So it's absolutely important to write certain things which are, well, I would say whatever you want to really understand it, you have to write it down. That's the only way that I really know that works, because when you're writing things down, you really pay attention to them. So if you restrict the domain of the tangent function to negative pi by 2 to pi by 2, then basically it is 1, 1. Then it is 1, 1, and onto, with its range as R, right? Now, instead of that, you could do anything like, for example, the tangent. You can say that actually the tangent function, can be restricted to basically any of the intervals, For example, you could go for negative 3 pi by 2 to negative pi by 2. You could go for example, negative pi by 2 to pi by 2. You could go for example, pi by 2 to 3 pi by 2, and so on and so forth, right? And the function would still be bijective, right? And its range, and the range in all cases would be R, right? So based on this, you can say that thus tan inverse can be defined as basically a function, whose domain is R, and the range could be any of the intervals, any of the intervals, for example, negative 3 pi by 2 to negative pi by 2, or you can say negative pi by 2 to pi by 2, or you can say basically pi by 2 to, for example, 3 pi by 2, etc., right? And so on, right? So these intervals give different branches of the, so the different intervals give different branches of the function, of the function tan inverse. Now the branch with the range, so basically the domain, we said that the domain would be R, and the range would be any of these, could be any of these intervals, but if I take basically negative pi by 2 to pi by 2, this interval here, so the branch with range negative pi by 2 to pi by 2 is called the principal value branch. It's called the principal value branch. The principal value branch of the function tan inverse. Of the function tan inverse, right? Now, so to sum it up, we can say thus we have basically the tan inverse function. The tan inverse is a function from R to the interval negative pi by 2 to pi by 2, and this is again, remember that this is the open interval of negative pi by 2 to pi by 2. And if you do the graph of the function, of course you will get basically this graph over here, which you have basically, this is the f of x is equal to tan x, and the inverse of the function would be f of x is equal to tan inverse of x. And you can see that the calculator gives you only the principal value branch of the function. Otherwise you would get something, actually something like this. You would get basically some function like this, meaning that basically, of course, all of these would be upside down or rotated 90 degrees clockwise or counterclockwise, I suppose I should say. I don't know really, but it depends on how you want to look at it. But then you would essentially have all of these branches over here. But since we restricted the domain of the function to negative pi by 2 to pi by 2 here, then that's the only, basically that's the only branch of the function that we are going to get as the inverse of the function, which is called the principal, I keep forgetting this thing, the principal value branch of the function, right? Okay, so that is basically that. Now, about the cot function, so let's go through the cot function as well in this video. Okay, so about the cot function, so what we have is that we know that the domain of the cot function, so let's take a look at the cot function first. Let's see what it is. I suppose I think we have enough time in this video for the cot function as well. So you know that basically when you say that, for example, cot of x is equal to cot of x, that is equal to basically the that tan of x is equal to sine of x divided by the cos of x, and the cot is the reciprocal of tan, which means that is the cos of x divided by the sine of x. And so what that means is that the cot function is not defined wherever I guess I want to change the background color here. Let me change my background color in just a moment. Okay, So now when you say when you say basically cot x, what that means is that you have cos x divided by sin x. So that means that cot x is not defined where sin of x is equal to 0. Now sin of x is 0 in basically different multiples of pi, meaning that 0 pi, 1 pi, basically 2 pi, 3 pi, 4 pi, 5 pi, and so on and so forth. That means that all the multiples of pi have to be taken out of the domain of this function, right? And basically, in order to be able to see that where the sine function is 0, so the sine, as we argued before, is always basically measured on the vertical axis here. So it's either positive 1 or it's negative 1 over here, and this is 0. So that is the sine function. Now the sine function, if you have some angles up here in the first quadrant or in the second quadrant, the sine of that angle will be some value between 0 and 1. If you have some angle between in the third quadrant or in the fourth quadrant, the sine of that angle will be some value between 0 and negative 1, right? Now the sine of x is going to be equal to 0 if x is equal to 0 degrees and 180 degrees, or basically 0 and pi. 0 and pi, basically the sine of x is equal to 0. That means that I can say that basically wherever you have integral multiples of pi, meaning that an integer multiplied by pi, that at those angles basically sine of x is going to be equal to 0. That means that I'm going to say that the domain of cot of x is basically all of the real numbers really, except for the integral multiples of pi, which means that I'm going to write this as r minus all x's, such that x is equal to n times pi, where n belongs to the set of integers. Meaning that, for example, you get 0 times pi, which gives you 0, in which case sine is 0. And if n is equal to 1, then 1 times pi is equal to pi, at which angle the sine of basically the sine of x is equal to 0. If you go for basically 2 pi, 3 pi, 4 pi, and so on and so forth, then you just keep moving around the circle, meaning that, for example, pi, and then 2 pi, and then 3 pi, and then 4 pi, and so on and so forth. And of course, n can be a negative integer as well, meaning that you could go in the other direction as well, and then still you would end up either at this angle or at this angle. In both cases, the sine is going to be equal to 0. Which means that the domain of the cos function is basically all the real numbers except for basically all of these x's that we specified here. Now, the codomain of the cot function is the set of real numbers, or the range of the cot function is basically equal to the set of real numbers, because if you take a look at the graph of the function, you'll be able to see that the function is going to give you basically all of these values from negative infinity all the way up to positive infinity along the y-axis. As you can see, the function goes from negative infinity all the way up to positive infinity. That's the cot function. And as we discussed before, the only difference between the cot function and the tan function is that, well, the orientation of the functions are different, meaning that the tan function basically between each of the periods of the function, for example, between these two vertical asymptotes that you see here, the tan function would start from negative infinity and go all the way up to positive infinity. Again, in this next period, it goes from negative infinity, goes to 0, goes to positive infinity, which means that which is an increasing function. The cot function is a decreasing function, meaning that from the very beginning of the period, starts from positive infinity, goes gradually to 0, not gradually, of course, very fast to 0, and then it goes to negative infinity, very, very fast. And then it keeps doing the same thing over and over again, right? So that's the range of your function, negative infinity to positive infinity. Now, so basically the cot function is basically this function over here, meaning that I can write the cot as a function from the domain is basically r minus all x's such that x is equal to n pi, and n belongs to the set of integers, and that to the set of real numbers, right? So that is the cot function. So let me go through the text quickly and see if we haven't missed anything here, or if we have missed something here. You know that the domain of the cot function, the code is the set, basically the set of all x's such that x belongs. So the same set, of course, you can write it that the set of all x's such that x belongs to the set of real numbers, and basically x is not equal to n pi, where n belongs to the set of integers. That's basically the same thing. Here we have excluded these values of x from R, and here we have basically put the whole thing together, and this goes to the set of real numbers, and this is the cot function. So it means that the cotangent function is not defined for integral multiples of pi. So this means that the cot function is not defined for the integral multiples of pi, right? If we restrict the domain of the cotangent function to, for example, 0 to pi, then it's bijective with the range R. So we can, of course, you can see very clearly here that the cot function is, of course, is not 1, meaning that, of course, it's an onto function. There is no problem with that, but it is not 1. Well, I just said something about this function which might not be completely true. So assuming that I don't restrict the domain of this function to anything, basically looking at the function itself as it is, the function is actually not onto either, meaning that basically when you talk about an onto function, what that means is that every basically you need to make sure for an onto function we say that basically an onto function is the kind of function where every member of the codomain, meaning that, for example, let's say that you have some set x over here, some set y over here, and for example, let's say you have x1, you have x2, you have x3, you have y1, you have y2, you have y3, and you have y4, right? Suppose that x1 is mapped to y1, x2 is mapped to y2, and x3 is mapped to y3. Now this function is 1, 1. There is no problem with being 1, 1. But the function is not onto because because in the codomain of the function there is an element y4 which is not the image of any element in the domain of the function. And what that means is that well, the function is not onto. A function which is onto is the kind of function where every element in the codomain of the function, not in the range of the function, but in the codomain of the function, that every element in the codomain of the function is an image of some element in the domain of the function. Now there is a problem here with this function, and with the function basically f of x is equal to cot x, and the problem is that basically here, as you can see, and the problem here is that basically if I say that the codomain of the function is basically, for example, all of the members of the set R, for example, right? If I say that, then basically R, since the function is periodic, then for example you can basically think of some element of the codomain of the function, for example 6, and 6 is basically, as you can see, is the image of this element in the domain of the function. It's also the image of this element in the domain of the function. It's also an image of this element in the domain of the function. So the function as it is, it's not really, it is of course not 1, 1, right? So there is no question of being onto either. I don't really know how to classify this function, but at any rate, the function has to be basically restricted in some way, so that the function becomes onto and 1, 1. And what that means is that now if we restrict the domain of the cotangent function to 0 to pi, for example, if I restrict the domain of the function to 0 to pi, meaning that if I go from 0 to pi over here, from 0 to pi, then the function is 1, 1 and onto. There is no problem with being 1, 1 because every basically distinct element of the domain of the function is mapped to a unique element in the codomain of the function. There is no problem with that. And also every element that you can find in the codomain of the function is the image of some element in the domain of the function. And then because of that, basically based on that logic, then your function is 1, 1 and onto. Otherwise the function is kind of well, I don't really know how to think about that sort of function. It's just not meaning that, for example, if I think about some function like, for example, f of x is equal to sine x. If I want to think about some function like, for example, f of x is equal to sine x, then of course this function is not 1, 1. And is not onto either, because if I restrict if I take the codomain of this function as the range of the function, for example, if I assume that, for example, the codomain and the range of the function are both the closed interval -1 to 1, right? So forgetting about all of these values, just thinking about -1 to 1. Even in that case, the function, for example, the positive 0.5, you can see that it's some element over here that has been mapped to this input. Also, it's been mapped to this input. Also, it's been mapped to this input. So it's just, and that happens because the function is periodic, right? So, well, of course, and I think, and I suppose you could say that when a function is not 1, 1, it's not onto either, because well, let's not go anywhere with this thought, because I don't know where the thought is taking me, and we don't really have to think about that. But basically, it's important to be aware of the fact that basically, for example, if you say that, for example, a function f of x is equal to suppose that you have a function f of x is equal to x. Now, suppose that f is a function from R to R, right? If f is a function from R to R, then of course you can say that the function is onto, and also the function is 1, 1. So the function is 1, 1 because every member of the domain of the function is basically mapped to a unique element in the codomain of the function, and meaning that any input that you take here is mapped to some element here, so you have no problem with being 1, 1. So 1, 1 is taken care of, and it's not like, for example, you have a sine function where, for example, and so, well, basically the problem of 1, 1 is being taken care of. We have no problem with that. Onto means that every element that you find here is the image of some element in the domain of the function, which is of course the case, meaning that any element that I take here, suppose that I take this element here, any element that I take here, I can trace it back to the graph of the function, and then the function gives me an input which can be used in order to get to that element. So the function is onto, right? But when it comes to a periodic function, suppose that I have a periodic function, for example, something like this, and suppose that it's a completely sinusoidal function, right? Now, basically some element in the range of the function, when I want to know if the function is onto, then I can trace it back over here, 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 and so on and so forth, all the way up to positive infinity, all the way up to negative infinity, which is a little bit, again, I don't really know how to think about that sort of thing. If you can of course share your thoughts with me on this, right? Now, I need to end this video here, and we will continue this in the next video. Thank you.